Hello dear students. Now in this video we are going to discuss about energy in simple harmonic motion. Energy in simple harmonic motion from the chapter oscillation. Okay, the topic name is energy in simple harmonic motion. Right. Suppose let us consider a particle executing simple harmonic motion. About the main position O and between the points A and B. That is, the particle move from O to A, then A to O, again O to B, then B to O. Okay, so this is a simple harmonic motion. So there is a particle which executes simple harmonic motion from the point O. Here the point O is called, or this position is called equilibrium position. Equilibrium position or mean position. Mean position, right. The positions A and B are called extreme positions. Extreme position 1 and this is extreme position 2. So the particle executing simple harmonic motion, it starts from mean position. That particle executes simple harmonic motion in between these two extreme positions. Okay, A and B are extreme position and O is a mean position or equilibrium position, right? So whenever the particle executing simple harmonic motion, there is a restoring force acting on the particle. The restoring force is acting on the particle which is executing simple harmonic motion, right? Due to this, the particle possesses potential energy. The particle possesses potential energy. Okay, if the particle executes simple harmonic motion, the particle possesses potential energy due to the restoring force acting on it, right? And also it possesses kinetic energy due to its motion. Okay, in the simple harmonic motion, the particle possesses both potential energy and also kinetic energy. The potential energy is due to the restoring force acting on the particle, and kinetic energy is due to its motion. Okay, due to the motion, it possesses kinetic energy, and due to the restoring force acting on the particle, it possesses potential energy. Right. Therefore, the total energy possessed by the particle which executing simple harmonic motion is equal to, suppose let it be E, and which is equal to U plus K. That means the sum of potential energy and kinetic energy possessed by the particle gives the total energy of the particle. Total energy of the particle. So in this topic, we are going to derive or calculate the total energy possessed by the particle when it undergoes a simple harmonic motion, right? First, what we want to do, first we need to find out the potential energy possessed by the particle, then kinetic energy. Okay, then only we can calculate the total energy possessed by the particle, right? Okay, we know that the definition of simple harmonic motion is that when the particle executes a simple harmonic motion, the restoring force acting on the particle is always directly proportional to the displacement of the particle, okay, which is always directed towards the mean position. Which is always directed towards mean position. That is, F is proportional to X. From the definition of a simple harmonic motion, F is directly proportional to X. It means if the particle executing simple harmonic motion, there is a restoring force acting on it. The restoring force acting on the particle is always directly proportional to displacement of the particle from the mean position, and this force is always directed towards the center, towards the equilibrium position or mean position. Towards the equilibrium position or mean position. So F is proportional to X, or F is equal to minus K into X. Minus K into X. Here K is force constant or spring constant. force constant or spring constant, right? And it is given by m into omega square, where m mass of the particle and omega angular velocity of the particle or angular frequency of the particle, angular frequency of the particle. So these two values are constant for a given particle. For a given particle which undergoes simple harmonic motion, right? So K is force constant or spring constant. It is given by m omega square, right? Here there is a negative sign in this equation. The negative sign indicates force and displacement are in opposite direction. Opposite direction. Okay, in simple harmonic motion, the restoring force acting on the particle is always directed opposite to the direction of the displacement of the particle. Okay, it is denoted by negative sign. So F is directly proportional to x from the definition of a simple harmonic motion. Therefore, F is equal to minus K into x. The negative sign indicates force and displacements or acts opposite direction, and K is force constant or spring constant. It is given by K is equal to m omega square. M omega square. Right. Here F is spring force or restoring force. Restoring force. Or otherwise spring force. Spring force. Right. And this restoring force does work on the particle which executing simple harmonic motion. Okay, so the restoring force is always does work on the particle which execute a simple harmonic motion, right? And work done by the restoring force, on the particle during a small displacement, that is dx, is given by dw is equal to minus f into dx. A small work done by the restoring force on the particle which executing simple harmonic motion during small displacement, that is dx, is given by dw is equal to minus f into dx. Minus f into dx. Already I told the negative sign indicates force and displacement are in opposite direction, right? And this work done is stored as potential energy in the particle. Okay, the work done by the restoring force is stored as potential energy in the particle. Potential energy in the particle. So potential energy du is equal to minus f into dx. Du is equal to minus f into dx. Right? What is f? Restoring force. Restoring force is given by minus k into x. Substitute f formula here. Then potential energy du is equal to minus of f minus k into x into dx. Therefore, du is equal to minus into minus a plus. So, kx into dx. Kx into dx. Right. So, this equation gives the small potential energy possessed by the particle during small displacement dx. During small displacement dx. Suppose the total potential energy possessed by the particle during the displacement of x is given by u is equal to integration of du. Okay, by integrating this small potential energy, we can get the total potential energy possessed by the particle during the displacement of x. Here the limit is taken from 0 to x. 0 to x. Right? Then u is equal to integration of a limit from 0 to x, and du is equal to kx into dx. What is k? Force constant or spring constant. So this is constant value. Constant value we can't integrate, so take outside. So therefore u is equal to k into integration of limit 0 to x, x into dx. Right. Integration of x into dx, x square divided by 2. The limit 0 to x. Right. After substituting upper limit and the lower limit, we can get u is equal to of k into x square. U is equal to of k into x square. Right. Okay, already we know that k is equal to m omega square. Therefore, u is equal to of m omega square into x square. So this is an expression for the potential energy possessed by the particle, okay, executing simple harmonic motion. Okay, and this equation, I mean this potential energy is continuously varies with the displacement. Continuously varies with the displacement. So this potential energy is, I mean potential energy of the particle due to the variation of the displacement of the particle. So whenever the displacement of the particle in simple harmonic motion changes, the potential energy of the particle also changes. Potential energy of the particle also changes, right? So here the displacement of the particle at every instant changes. It is given by the expression x is equal to a sin omega t. Already you know about that. The displacement of the particle in simple harmonic motion at any instant is given by x is equal to a sin omega t. So this is potential energy of the particle executing simple harmonic motion in terms of displacement. In terms of displacement. Now the same potential energy expression can be obtained in terms of time period. In terms of time period. That is u is equal to of k x square or u is equal to of m omega square x square, where x is equal to a sin omega t. Therefore u is equal to of m omega square. Instead of x we can write a sin omega t. So a sin omega t the whole square. A sin omega t the whole square. So u is equal to of m omega square into a sin omega t the whole square, a square sin square omega t. Okay, u is equal to of m omega square, a square sin square omega t. So this is the potential energy of the particle in simple harmonic motion with respect to time. And this is potential energy of the same particle in simple harmonic motion with respect to displacement. Okay, here displacement is continuously changes with the time, so the potential energy value also changes. So this is potential energy in terms of displacement, and this equation is in terms of time period. From both equations we can calculate the potential energy of the particle in simple harmonic motion, right? And next, kinetic energy. Kinetic energy in simple harmonic motion. We know that the general expression for kinetic energy is of m v square. Of m v square, where m mass of the particle and v velocity of the particle. Velocity of the particle. In simple harmonic motion, the velocity of the particle also continuously changes with the time. Okay, we know that velocity is nothing but the rate of change of displacement. Velocity is nothing but the rate of change of displacement. Or v is equal to d divided by dt of displacement in simple harmonic motion is given by x is equal to a sin omega t. Okay, a sin omega t. Right, therefore v is equal to differentiation of a sin omega t with respect to time, a into omega into cos omega t. A is constant. Okay, in given simple harmonic motion, it's an amplitude. A is amplitude. So amplitude value is a constant. So we can't differentiate. So take outside. D divided by dt of sin omega t gives omega into cos omega t. Omega into cos omega t. So the velocity of the particle in simple harmonic motion at any instant is given by v is equal to a omega into cos omega t. Right? And another one expression also there, that is v is equal to omega into square root of a square minus ax square. So both the equations are gives the velocity of the particle in simple harmonic motion. Right? Now substitute v is equal to omega into square root of a square minus x square in this equation. Okay, then the kinetic energy of the particle is equal to of m instead of v omega into square root of a square minus x square the whole square. Right. So that is equal to of m omega square root of a square minus x square the whole square a square minus x square. A square minus x square. So this is kinetic energy of the particle in simple harmonic motion in terms of displacement. In terms of displacement, right? And in terms of time period, just you substitute v is equal to a omega into cos omega t in this equation. Okay, if we substitute v is equal to omega into square root of a square minus x square in this equation, we can get the kinetic energy of the particle in terms of displacement. In terms of displacement. Suppose if we substitute v is equal to a omega into cos omega t in the same expression, we can get the kinetic energy of the same particle in terms of a time period. In terms of time period. That is, kinetic energy is equal to of m instead of v a omega cos omega t. Okay, the whole square. Right. Therefore, of m a square omega square into cos square omega t. Cos square omega t. So this is kinetic energy expression in terms of time period. Okay. So kinetic energy value known and potential energy value also known. Okay. From them we can calculate the total energy of the particle in simple harmonic motion. Right. The total energy in simple harmonic motion. Right, the total energy is denoted by E, which is equal to sum of potential energy and kinetic energy. Sum of potential energy and kinetic energy. Right, potential energy expression in terms of displacement, where is that? Of m omega square x square. Of m omega square x square. Right, and kinetic energy of the particle in the simple harmonic motion in terms of displacement is of m omega square of a square minus x square, right, plus of m omega square of a square minus x square, right. Therefore, of m omega square x square plus of m omega square into a square minus of m omega square into x square, of m omega square into x square. Here plus of m omega square x square minus of m omega square x square get cancelled. Okay, therefore total energy of the particle in simple harmonic motion E is equal to of m omega square a square. Right. So this equation is obtained from the potential energy and the kinetic energy of the particle in terms of displacement. In terms of displacement. Right, and another two equations also there, that is in terms of time period. Okay, kinetic energy in terms of time and potential energy in terms of time equation also there. By adding these two equations, again we get E is equal to of m omega square a square. Okay, let us prove. Right, the potential energy of the particle in terms of time period is given by of m omega square a square sin square omega t. Sin square omega t. And kinetic energy of the particle in terms of time period is given by of m omega square a square cos square omega t. Cos square omega t. Therefore, total energy is equal to potential energy plus kinetic energy. Potential energy of m omega square a square sin square omega t plus kinetic energy of m omega square a square cos square omega t. Cos square omega t. In this two term of m omega square a square is a common. So take outside. Of m omega square a square of here sin square omega t plus cos square omega t. Right, sin square omega t plus cos square omega t 1. Therefore, the total energy of the particle in simple harmonic motion E is equal to of m omega square a square. Okay. So from this equation, that is the total energy of the particle in simple harmonic motion, it is clear that the total energy value is always a constant. Okay, this equation obeys the conservation of energy. Law of conservation of energy. Conservation of energy. Here, the amplitude of the particle in simple harmonic motion, omega angular frequency, and m mass of the particle. Okay, for a given particle which executing simple harmonic motion, these three values are constant. So the total energy value also constant. So in simple harmonic motion, the potential energy of the particle, kinetic energy of the particle in simple harmonic motion continuously changes with the displacement and also with the time. Okay, but the total energy of the particle remains a constant. The total energy of the particle remains constant. Right now, the variation of potential energy with respect to time and kinetic energy, variation of kinetic energy with respect to time can be represented with a graph, a simple graph. Right. First, the variation of potential energy with respect to time graph. Okay, the graph is like this. Like this. Right here, what is capital T? Time period of the particle in simple harmonic motion. What is meant by time period? The total time taken by the particle to complete one oscillation or to complete one vibration is known as a time period. Okay, time period. So this is variation of a potential energy of the particle in simple harmonic motion with respect to time. Okay, at time t equal to 0, the potential energy of the particle is 0. If for time t is equal to t by 4, potential energy is maximum. At a time t is equal to t by 2, again potential energy value is 0. If for time t is equal to 3t by 4, potential energy maximum. If time t is equal to capital T, again the potential energy value is 0. So this is variation of a potential energy with respect to time graph. Next, variation of kinetic energy with respect to time graph. Variation of kinetic energy with respect to time. Like this. 0, t by 2, here t. Okay, at a time t is equal to 0, the kinetic energy of the particle is a maximum. The kinetic energy of the particle is 0. At time t is equal to t by 4, kinetic energy value 0. If time t is equal to t by 2, again the kinetic energy value maximum. For time t is equal to 3t by 4, put a kinetic energy value 0. Time t is equal to 1 time period, again the kinetic energy value is maximum. Kinetic energy is maximum. So this is variation of a kinetic energy of the particle in simple harmonic motion with respect to time. Next, variation of a potential energy, kinetic energy and total energy with respect to time graph. Actually, the total energy does not changes with the time. Kinetic energy and total energy. Right, this is potential energy, variation of potential energy with respect to time. Okay, this curve is kinetic energy variation with respect to time, and this is total energy. So the total energy of the particle in simple harmonic motion remains constant, whereas the potential energy and the kinetic energy of the particle is continuously changes with the time. Okay, so this is common graph for potential energy, kinetic energy and total energy with respect to time. Next graph, the variation of potential energy, kinetic energy with respect to distance or with respect to displacement. With respect to displacement. Right, so this is potential energy and this is for kinetic energy. Here the graph is drawn between the displacement and the energy. Displacement and energy. Right, if the displacement x is equal to 0, the displacement x is equal to 0, the potential energy value is 0. Potential energy value is 0. Whereas kinetic energy value is maximum. This is kinetic energy variation graph. Okay, if the displacement of the particle is 0, potential energy value is 0, whereas the kinetic energy value is maximum. Kinetic energy value is maximum. If the displacement is equal to amplitude, that is plus a, the kinetic energy value is 0. Kinetic energy value is 0, whereas the potential energy is maximum. The potential energy is maximum. It means at the mean position, potential energy value is 0, but kinetic energy value is maximum. But at the extreme position, first extreme position, kinetic energy value is 0, whereas the potential energy is maximum. Right. In second extreme position, that is x is equal to minus a, again kinetic energy value is 0, kinetic energy 0, whereas potential energy is maximum. Potential energy is maximum. So at the extreme positions, potential energy maximum. At the mean position or equilibrium position, kinetic energy maximum. But in all position, the total energy remains constant. The total energy of the particle in simple harmonic motion remains constant. So this is a graph which is drawn between potential energy, kinetic energy and total energy in terms of displacement. Right. Thank you, student. So far we discussed about energy in simple harmonic motion from the chapter oscillation. Right. Please you go through this topic. If you have any doubt, you call me. Right. Thank you, student. We will see in the next class.